And so we start not with a trig problem, but just sort of a warm-up problem. And hopefully we should finish it before the end of class. No, it's not that bad. All right, so find all parabolas. Oh, there's a lot of parabolas. But all parabolas, y is equal to ax squared plus bx plus c, which has a certain set of properties. It goes through a particular point 0, 0, and another particular point 3, 3, and it has to be tangent to the line y equals 2x minus 4. So, what's going on? I have to pass through a point here. I have to pass through another point somewhere over there-ish. And then there's this line, y equals 2x minus 4. And so I want to be able to satisfy all three conditions. I have a pass through those 2 points, and I'm tangent to those, or to this one line. It's not so hard to believe that it's possible. I mean, we can sort of eyeball in something that does it. I mean, maybe something that looks like that-ish, maybe. I don't know. We'll see where it takes us. Now, some of these constraints are not so hard. In fact, we have essentially, if you think about A, B, and C, that means there's 3 things for us to play around with. We have to find 3 things, A and B and C. So every time I have a piece of information, that helps me narrow down my search. And I have 3 pieces of information, the 0, 0, the 3, 3, and the tangent line. Okay, so let's just work through them. So we pass through 0, 0. What does that tell us? Well, if you plug 0 in for x, you'll get 0 for y. So 0 is equal to a times 0 squared plus b times 0 plus c, which means, c equals 0. Well, that was quick. We're 1/3 of the way done. Nice. Nice. I suspect the next 2/3 will be more challenging. Okay. Well, now let's use another fact. We pass through the point 3, 3. So I can now plug 3, 3 in. And I'm going to use the fact that c is 0. So, in fact, let's just cross it out because now we know that c is 0. So we're going to get that 3 is equal to a times 3 squared plus b times 3. And since everything has a 3 in it, we might as well divide out. 1 is equal to 3a plus b. So whatever a and b are, they have to satisfy this relationship. 3a plus b equals 1. Another way I can write this is to say, hey, I can rewrite this as b equals 1 minus 3a. So if we take our parabola now, we say our parabola looks like y equals ax squared plus 1 minus 3a times x. So using the fact that we pass through 0, 0 and pass through 3, 3, we have 2 pieces of information which essentially help us knock out 2 of our a, b, and c. So we're down to just one parameter we don't know yet. We're down to a. We need to figure out a. And of course we haven't used the fact that we're going to pass through the line, we're tangent to the line 2x minus 4. Now let's think about how we can use this fact. So we're tangent to this line y equals 2x minus 4. How do we use that? I mean, it's not so clear that there's an easy way to use that information. Because what don't we know? We don't know where it's tangent at. Because there's a lot of points on this line. And we haven't said which one is the right one. There's some point where it's tangent, but we don't have an explicit thing that says, I'm tangent here. But let's think about things that are true. So at the point where it's tangent, what must be true? Are some things true about our slopes, right? So at our point of tangency, which we don't know. But we do know the following. We would have to have that the slope of our parabola would have to match the slope of our tangent line, which of course we change slopes to more fancy words like derivatives. So the derivative, what's our derivative of ax squared plus 1 minus 3a times x? 2ax plus 1 minus 3a. So at our point of tangency, it has to be the case that our derivative, 2a times x plus 1 minus 3a, had better be the same as the slope of our line. Well, what does this let us do? Well, from here, we can solve for x. So I'm going to move the 1 minus 3a across so that we have 2a times x would be equal to 3a plus 1, because the minus 3a becomes a plus 3a. Then I'm going to take a minus 1 plus 2 to make a plus 1. Or x equals 3a plus 1 over 2a. So that says this is where it happens. But it's kind of an unsatisfying answer. It's an answer in terms of a. We still don't actually know because we don't know what a is. But what have we used? We've used that at the point of tangency, what's true? We said the slopes match. There's something else that has to happen at the point of tangency. The functions have to match. So in other words, at the point of tangency, the point on the parabola, that y-coordinate has to be the exact same as the y-coordinate of the line. Good news, we have the x-coordinate. So, what happens? We're going to plug this x-coordinate into our parabola. So we're going to get a times 3a plus 1 over 2a squared plus 1 minus 3a times 3a plus 1 over 2a. And that's going to be the same as if we plug it in to the line, 2 times 3a plus 1 over 2a minus 4. Now what's the good news? The good news is this is one equation and just one variable. Just a. That's it. The bad news is we've got to solve this. Well, we're patient. We're gonna work our way through this. If we square here, this first term, that would be 9a squared plus 6a plus 1. What would be the denominator? 4a squared. But notice I already have an a upstairs, so I'm going to put this as just a 4a because the a's will cancel. Plus, here I have 1 minus 3a, here I have 3a plus 1. I could have written this 3a plus 1 as 1 plus 3a. So it's 1 minus 3a, 1 plus 3a. So that's the difference of squares. So that becomes 1 minus 9a squared over 2a. On the other side, I can cancel off a 2, so that's a 3a plus 1 over a, and then there's a minus 4. What's our next step? Yeah, so we can do something, we'd like to get rid of the denominators. Now, one thing you could do is you could say, let's make all the denominators 4a, which would help us. The other thing to do is to just say, look, I don't even want any fractions. I just am fraction averse. I've learned my lesson. I'm not going to mess with another fraction again. I've been bitten before. So, what can I multiply by that'll gets rid of all my fractions? 4a. So if we multiply everything by 4a, in the first term, what are we left with? 9a squared plus 6a plus 1. The second term? Yeah. So notice the 2a and the 4a leaves us with the 2. So you multiply everything here by 2. So that's a 2 minus 18a squared. For the next term, what do you do? Yeah, the a's cancel, so it's 4. So it's 12a plus 4. The last term, minus 16a. Now, from here, let's move over to this stage. All right, so from here, what do we need? Well, let's gather all our terms. Let's move everything over to the right-hand side. So let's look at our a squareds. How many do we have? We have 9a squared and minus 18a squared, but that's going to move across and become 9a squared, right? Because it's 9 minus 18. It's negative 9, positive 9. All right, how about our a's? Well, we have a 12a, let's see, minus 16a. Yes? Did I do that right? All right, what's 12 minus 16? It's negative 4. And I'm going to subtract 6a. So what does that leave me with? Minus 10a. Okay, so I've gone the a squareds. I've gone the a's. And then I have 1 plus 2, which is 3. When we bring it over, there's already 4. That leaves me with a 1. All right. Now, can we solve that? Hopefully. Well, what do we want to be true? We hope it factors. Does it factor? Yeah. Well, you're very suspicious. It's like everything's factored so far. You know, there's going to be that one time when something doesn't factor, and you'll be like, oh, well, that's unexpected. That's different. Okay, so 9a squared minus 10a plus 1, how does it factor? 9a minus 1, a minus 1. Which leaves us with two possibilities. What's a? 1 or 1/9. Now, that's not our answer. What's our answer? Well, remember, what were we asked? We're asked to find a parabola. So our answer should be what? Should be a parabola, because we were asked to find a parabola. So I'm going to take this, and how do we get our parabolas? Well, the good news is once we have a, we plug it in, because this is our parabola in terms of a. So let's do 1 first. So we get y equals 1 times x squared, so that's x squared. Then 1 minus 2. Well, 1 minus 3, which would be negative 2. So x squared minus 2x. And another one, 1/9. 1/9 x squared. And then we have to have 1 minus 3/9. Well, 3/9 is a third. 1 minus a third would leave us with plus 2/3 x. So those are our two parabolas. I guess you could say all parabolas with this property. All right. Now this was a challenging problem, and I will be completely honest with you. This is more challenging than what we would want to put on the exam. But I think you should see challenging problems, because I think that there's a lot of beauty. Because initially it's like, okay, the 0, 0, we're making progress, the 3, 3, we're making progress, and then it feels like, we're stalling out. But you keep exploring, you keep trying stuff. We're going to give you things that can be done. All right, good. Any questions on that one? Well, let's do some more problems. Okay, so a 10-foot ladder is leaning against a wall. And so I suppose we should try to draw this. So we just quickly draw a ladder here. So here's our ladder. Now, you don't have to have a realistic looking ladder, but it helps visualize, right? Okay, so let's say that this looked like a ladder, and it's leaning against a wall. So here's our picture. It's a 10-foot ladder. It leans against a wall, and there's an angle between the ladder and the wall. Maybe that's not the best way to draw it. So we're gonna make our picture much more simple. So here we go. Here's the wall, here's the floor, and here's the ladder. Not as exciting, but okay. All right, but that's certainly true. And we have theta is the angle between the ladder and the wall. So that means there's this angle right here. This is theta, ladder, wall. And suppose that x is the distance from the bottom of the ladder to the wall. Well, here's the bottom of the ladder. So the x was this part here. So over in this picture, this is our distance x, and our angle theta is coming in over here. This is the theta that you can't quite see very well. And there's a question. Find the rate of change of x with respect to theta for an arbitrary value of theta. Now we see a key word here, rate of change. We see that, what do we think? Derivative. So we're asked to find the derivative. And we say, look, the derivative of what? It says of x with respect to theta. So that's code for change in x with respect to theta. So that's what we're looking for, is dx d theta. So what needs to happen? Well, in order for us to take a derivative, what we need to do is to say, all right, what's the relationship? So in the picture here, we say, all right, we know a couple of things. We know we already labeled the distance from the bottom of the ladder to the wall. That's x. We labeled the angle theta. There's something that we haven't labeled yet. What hasn't been labeled? The ladder. What's true? It's 10 feet. So now we take a look at our picture and say, okay, let's assume that we live in a well-built house. So that this is actually a nice right angle. It's a pretty reasonable assumption. We have an angle. We want to relate it to the opposite side, and we know the hypotenuse. So what relates everything together? Sine. So sine of the angle theta is the opposite side divided by the hypotenuse. Now, I want to know dx d theta, so that means I want to write x as a function of theta. So I want to get x by itself. It's not so hard to see what to do. What should we do? Multiply by 10. So we have that x is equal to 10 sine theta. So now we say, all right, now I know how I can write x with respect to theta. Once I have x with respect to theta, I can now say, well, what's the change in x? What's the rate of change of x with respect to theta? So we're ready to write our answer. So that means we're taking the derivative. And here, our variable name is theta. So what's the derivative of 10 sine theta? 10 cosine theta. Because last time, we saw that the derivative of sine is positive cosine. All right. Well, that was not so bad. Good. And if you like ladder problems, stick around. We're going to do a lot of ladder problems in the next couple of weeks as we go on. So the next problem. A particle moves according to the following function. So we can think of this, it's moving through space, and so s of t is, we'll think of that as our position at any given time. So when I say space, we're right now in the case where when we move along the line. Because we don't have enough tools yet to handle more things. But don't worry, as we go through calculus, we'll develop more tools and we'll get to do things which are more interesting. So right now, we have, again, here's our space, and our particle is doing some sort of motion, moving around. I don't know what it's doing, but it's moving back and forth. Okay? That's how you should think of it. So the question, determine for which values of x, typo, t, with 0 less than or equal to t less than or equal to 2 pi, the particle moves to the left, moves to the right, and is stationary. So what I have is I have information about position, and I want to talk about information about how it's moving. So how do I go from information about position to information about movement? Derivative. So when you take the derivative of position, the result is what we call velocity. So we need to take a few things. Let's take a minute to recall. So S of t is position. S prime of t is velocity. And now it says something. Moves to the left, moves to the right, and is stationary. Well, how does that translate into velocity? What does move to the left mean? Sorry, what? Negative velocity. Okay. So move to the left means S prime is negative. Well, why? It says our change in our location is going down. It's a negative change, which means as time moves forward, the location we're at is going to our left-hand side, which means we're decreasing. When do we move to the right? When we're positive. S prime positive. And when are we stationary? When we're equal to 0. So oftentimes that transition from moving to the left, moving to the right, it's just like, let me pause for just a second. Okay, now I'm going to switch directions. So this really is a question about the derivative, what's happening with the derivative. You're probably thinking, oh, wow, another derivative problem in calculus? You'll get a lot of those. A lot of the problems involve derivatives. So what is our derivative in our case? So our function is t plus 2 sine t. Our derivative is 1 plus 2 cosine of t. So our next step is to say, now I'm looking at the interval between 0 and 2 pi. I need to figure out positive, I need to figure out negative, and I need to figure out 0. Because the function 1 plus 2 cosine is a nice function, this is a continuous function, it's not going to somehow spontaneously jump from a negative to a positive without going through 0 in the middle. So oftentimes what's best is to start with the stationary. So this gives you a lot of insight. So we're going to start with our stationary and then figure out what's happening on either side. So when does 1 plus 2 cosine of t equal 0? What's another way to write that? Cosine of t is negative 1/2. Now, it might help to recall that we can do trig with the unit circle. And when we're looking for cosine, in terms of the unit circle, the cosine corresponds to the x-coordinate. So cosine t equals negative 1/2 says that you want to come here at x equals negative 1/2. And that'll be your cosine t. So we're looking for two angles. One angle that's a little bit more than 90, a little less than 180. And another angle that's more than 180, but not quite 270. So what are the angles? Well, one thing you can do is sort of start by saying, if you're not sure, you can say, what about this angle right here? When does cosine equal 1/2? Do you know that angle? Pi what? Pi over 3. So one way you can think of it is you can say, look, I'm going to go pi, then go back pi over 3. So the first angle would be 2 pi over 3. So again, I'm thinking like, okay, I know if I just go pi over 3 here, that would give me something where I get cosine equals 1/2. So I'm thinking about, I go pi first, then I walk back pi over 3. By symmetry, I'll be at a place where I've just moved directly across. So that's the 2 pi over 3. Where's the next one going to be? Well, you can do, one of the ways you can do it is you can say, look, it's directly opposite over here. Another way you can do it is say, look, I'll go pi, then I'll go 1/3 pi more. So 4 pi over 3. So those are my 2 times. Now, those aren't the only 2 angles. There are, in fact, infinitely many times when cosine is equal to -1/2. But I'm only interested in the angles between 0 and 2 pi. Why am I only interested in the angles between 0 and 2 pi? Yeah, because it told me to be interested in those angles. So, we now say, all right, we're going to make a line here. I have times 0. I have 2 pi over 3, 4 pi over 3, and over here is 2 pi. So this is t. And I now know that at 2 pi over 3, that these are the times where we're stationary. Stationary at those 2 moments. What's left for us to do? Well, the left and the right. So for that, we say, okay, once I know where I'm 0, because I'm continuous, what's going to be the case is that if I look at any interval, it's always got to be the same sign. So if it's positive anywhere in between here, it's positive everywhere in between here. That's the nice thing about continuity, because I can't go from positive to negative without crossing through 0. That was our intermediate value theorem. That comes with continuity. So to know what's happening, I just have to pick any convenient angle between 0 and 2 pi thirds. Does anybody have a convenient angle between 0 and 2 pi thirds? How about 0? That's between 0 and 2 pi thirds, right? What happens when you plug in 0? You get 1 plus 2. Is it positive or negative? Positive. So that says S prime here is positive. All right, 2 pi over 3 to 4 pi over 3. Is there a convenient angle? Pi. Pi is convenient. Cosine of pi is -1. So S prime of pi will be 1 plus 2 times -1, which means that S prime of pi is -1. But I don't really care about the value of -1. I care about the sign. I saw the sign, and it opened up my eyes. I saw the sign. Between 4 pi thirds and 2 pi, is there a convenient angle? 2 pi is pretty convenient. Plug in 2 pi. Are we positive or negative? We're positive. So, what can we say? Well, between 0 and 2 pi thirds and 4 pi thirds and 2 pi, we're moving where S prime is positive, we're going to the right. And then for S prime less than 0, that's between 2 pi thirds and 4 pi thirds, that's to the left. So I guess I should write that down. So left is, I'll say 2 pi thirds comma 4 pi thirds. I'll use the interval notation. And then right between 0 and 2 pi thirds and 4 pi thirds and 2 pi. And that would be the answer. Okay. And if you like this type of problem, great news. We've got more coming. We have a lot more coming. All right. The next one. Suppose that we have a way to control a particle so that its position at a given time t is given by S of t is at sine t plus b cosine t, where we can pick a and b. So we have a machine, and it's controlling this particle. And depending upon how we set the machine, the particle can do different things. Well, what do we want? Well, we want to ensure that its velocity at time pi over 2 is 2, that its acceleration at time pi is 5. Okay, so that gives us information about what we need to do. And given that that's the case, the question is, what would be the position of the particle at time pi force? So there's sort of 3 things going on here. There's velocity, there's acceleration, and there's position. And we have the position function. So we might say, hey, well, shouldn't this be an easy problem? All I have to do is plug in pi force and I'll get the answer. The problem is that we can't plug in pi force yet, because right now, if we plug in pi force, our answer will contain A and B, and we don't know what they are yet. So we need to use information to figure out what A and B are before we can just plug it in. So let's start thinking about what we have. We have a condition about velocity and a condition about acceleration. So velocity, what should I do to talk about velocity? Just take a derivative. So s prime of t. So how do I take the derivative of a times t times sine of t? What rule? What? Product rule, right. The a is a constant, so for that we just say, look, it comes along for the ride, but the t and the sine t, those are functions. So I'm thinking that's two functions multiplying together. So I would do it, so take the derivative of the first, so that would be 1 times the second, sine of t, plus the first, so that would be a times t, times the derivative of sine, which is cosine. What's the derivative of b cosine of t? Minus b sine of t. Remember, cosine has that weird thing where when you take its derivative, there's a negative coming in. So don't forget about that. The derivative of cosine, negative sine. Negative. Negative. All right. So, well, we could clean it up a little bit. We could say, for instance, we have a sine, and here's a sine. So we could write this as a times t cosine of t plus a minus b times sine of t. Because since we have an a sine t and a minus b sine t. Now, let's use the information that we have. We know that its velocity at time pi over 2 is 2. So that means if I plug in pi over 2 into the derivative, what comes out? I'll get 2 out, because that's what it means to say the velocity at time pi over 2 is 2. Of course, I could also plug pi over 2 onto this other side. So that would be a times pi over 2 times cosine of pi over 2 plus a minus b times sine of pi over 2. Well, let's clean it up. Cosine of pi over 2 is 0. And 0 is a very convenient number. It knocks off a lot of stuff. Sine of pi over 2? Is 1. So we can conclude from the velocity we get the following. Namely, a minus b had better be 2. Now we come to the second part, which is acceleration. What do I need to get to acceleration? Second derivative. First derivative is velocity. Second derivative is acceleration. All right. So a times t times cosine of t, it's a product rule again. So the derivative of the first, that'll be a, and I'll put a 1, times the second function, cosine t, plus the first, which is at, times the derivative of cosine, which I'll write as negative sine. And I'm paranoid about losing points. And so, to help me make sure I remember that this negative isn't a subtraction, at minus sine t, but it's a multiplication, I'm putting parentheses here. Because I want all the points. That's my goal. All the points. Okay, plus then a minus b, and coming here, derivative of sine is cosine. All right, well, we can clean it up a little bit. This would be, from this term right here, minus at sine of t. Then I have an a times cosine t and a minus b times cosine t. So that would be 2 times a minus b cosine of t. Now, what do we do next? And we plug in what? Yeah. Acceleration says, oh, it's a different time. It's at pi. needs to be 5. So 5 is equal to s double prime of pi. So that's minus a times pi times sine of pi plus 2a minus b times cosine of pi. Well, what's true about sine of pi? 0. Aha! 0, our friend. We like 0. Cosine of pi. What is it? Negative 1. Negative 1. So if you think about it in terms of the circle, the unit circle, pi is a half revolution, and so it's negative 1 comma 0 is the coordinate. So the cosine is negative 1. So we get that 2a minus b is equal to negative 5, because I can multiply both sides by the negative. So that's from our acceleration. So now what do we have? Well, we're in a situation which we should be really comfortable with by now. And by the time you get to Calc 3, you're going to be like, another one of these. And you're just going to whip it out in 30 seconds and just be like, okay, I know how to do these. So 2 equations, 2 unknowns. So what we do is we try to find a way to combine these equations to get cancellation. There's lots of ways to do it. My favorite way to do it, and you can use whatever way you like, as long as you get the right answer, I'm happy with whatever way you use. But it has to be something mathematically justifiable. Don't just be like, I tried something, I guessed randomly for an hour, and I came up with an answer. No. Systematic. So here, what I like to do is I like to think of ways to combine. So I can see, for example, that the b's are lining up very nicely. So if I were to subtract the 2 equations from each other, then I would get a lot of cancellation. So 2a subtract a would leave us with a single a. Minus b subtract a minus b cancels out. Negative 5 minus 2 gives negative 7. So we get a equals negative 7. Now once you have that, you can plug it into either one. So you could say I plug it into the first one. Minus 7 minus b equals 2. Then I can move the minus b across, I can move the 2 across. And if we do that, we'll get that b equals negative 9. All right. So a is negative 7 and b is negative 9. So what does that mean? Well, it means we go back to our position function. It says now we know a and b. So it's minus 7t sine of t minus 9 cosine of t. And to finish off, what were we after? The position at time pi over 4. So what's our last step? Plug in pi over 4. So s at pi over 4 is equal to negative 7 times pi over 4 times sine of pi over 4 minus 9 times cosine of pi over 4. Now, I think we can go just a little bit further. Do you know what sine of pi over 4 is? Square root of 2 over 2. Cosine pi over 4? Square root of 2 over 2. So here in the first one we get minus 7 root 2 pi divided by 4 times 2 is 8. The second one we'd have minus 9 root 2 over 2. And that would be our final answer. Okay. Good. So, one more problem. The half-angle formula for tangent is the following. So this is a fact from trigonometry. There's an identity. It says that tangent of half of x is 1 minus cosine of x over sine of x. And we want to use this to find the derivative of tangent of x over 2. And then there's the question of how does this compare with the derivative of tangent of x? Well, that's a good question. Well, let's just start here. So we're after the derivative of tangent of x over 2. And we say, well, I don't know how to take the derivative of tangent of x over 2, but because we have an identity, we can rewrite it. 1 minus cosine of x over sine of x. All right. Well, progress. Progress has been made. Now, the next question, can we take the derivative of 1 minus cosine x over sine x? Do we have the technology? Yes, we do have the technology. What's the rule we need? Quotient rule. Okay, so the quotient rule, it says what? Take the bottom term, which is sine of x, and times it by the derivative of the top. Well, derivative of 1 is 0, minus derivative of cosine of x, that's minus sine of x. Okay, so that's the bottom times the derivative of the top. Subtract the top term, 1 minus cosine of x, times the derivative of the bottom term. What's the derivative of the bottom? Cosine x. And divide all that by sine squared of x. All right. Well, that's nice. Well, let's see what we have. Well, minus minus makes plus. So we really have a sine of x times a sine of x. That gives us sine squared of x. Here we can distribute through. So we have a minus and then a cosine. So minus cosine of x. Then minus minus makes plus. Cosine times cosine. That would make cosine squared x all over sine squared of x. Well, what can we do? There's a sine squared here and a cosine squared there. Oh, those equal 1. Okay, so we end up with 1 minus cosine of x over sine squared of x. Huh. Okay. That's well, it's a true statement. So let's see if we can't rewrite this. What can we do? What can we do? Oh, someone's saying, hey, there's a 1 minus cosine squared, right? So you could downstairs. Now, you might say, hey, wait a second. You should stop, Steve, because that's an answer. And you're absolutely right. That is an answer. But let's probe a little bit. See if we can't rewrite it. 1 minus cosine x. And let's see. Downstairs, there'd be, someone was saying 1 minus cosine squared of x. Okay, so I guess everything cancels but the square, right? Is that how cancellation works? Like the 1 cancels with the 1, right? No? Yes? No? Yeah, it doesn't. That's not how cancellation works. Yeah. You gotta work a little bit harder. We don't want it to be too easy. We want it to be the right amount of easy. Okay. So this is 1 minus cosine x over 1 minus cosine x times 1 plus cosine of x. And you can cancel off 1 minus cosine of x. And you're like, cool, well, you're right, Steve, that was a much better answer. But no, we're going to keep going. We're not satisfied yet. We say, you know what? We really wanted to end up with an x over 2. We really did. And you might say, why did we want to do that? Well, we wanted to end up with an x over 2 because we started with an x over 2. So, let's think about this. Okay, all right, okay, here. I have an idea. We can write this as 1 over 1 plus cosine of 2 times x over 2. I mean, that's a true statement, right? Let's see. Was that going to be helpful? So 1 plus cosine of 2 times x over 2. And we're starting to think, all right, is there a nice identity? Well, it turns out, I'm going to make a little side note, that there's 6 trig identities that you need to get you from Calc 1 to Calc 3. I'm going to mention 2 of them, and then we're going to look at this, and then we're going to have a great, I see where you're going. So the 2 that I'm going to mention, sine squared theta. That's 1 minus cosine 2 theta over 2. Cosine squared theta is 1 plus cosine 2 theta over 2. Here, we have a 1 plus cosine 2 something. This can be our theta. So it's like, oh, it can almost become like a cosine squared. What's missing? The over 2 part, right? So what we're going to do is we're going to make it over 2, which means put a half here. But if I put a half there, where else do I have to put a half? Upstairs. So if we do this now, what do we get? Well, we get the half. I'll just write that in front. Then we have 1 over, and then this part becomes cosine squared of x over 2. But what's another way to write cosine 1 over cosine squared? 1 over cosine squared becomes secant squared. 1 over cosine is secant. 1 over cosine squared is secant squared. So this becomes 1/2 secant squared of x over 2. So that's the one I want. Why? Think about the derivative of tangent, because we're supposed to compare. Derivative of tangent, do you recall what it is? Secant squared. We just show that the derivative of tangent of x over 2 is 1/2 secant squared x over 2. So it's almost like when we took this derivative where there was this extra half, it was like we took the derivative before, left the inside alone, and then multiplied by half. Well, that's interesting. It'd be nice if there were a rule for this. If we had such a rule, you could say it would really change the story. So, well, let's talk about that rule next time. All right, that's it for today.